The integers and division. Of course, you already know what the integers are, and we have already done the lots of discussion upon the integers and the relative concept. But here there are some specific notations, terminology, and the theorems associated with these concepts, and which you may not know. So this form the basic of number theory. Vitally, many important algorithms today, like hash functions, cryptography, digital signatures in general, and in many applications, and also in online security purpose, there are lots of uses of the basics of number theory using these concepts. So here, first of all, we have to discuss the basics of the divides operator. The new notation 3 divides 12. It means to specify when an integer evenly divides another integer. Read as 3 divides 12. The not divides operator 5 divides 12. This is not possible, so here we have to use this cross line upon the vertical line, like 5 does not divide 12. To specify when an integer does not evenly divide another integer, read as 5 does not divide 12. Divides factor multiples. Let a b belongs to integers with a not equal to 0, and the definition is a divides b is congruent to a divides b. There is an integer c such that c times a equals b. So here the example, like 3 divides minus 12, this is true, but 3 divides 7 is false. If a divides b, then we say a is a factor or a divisor of b, and b is a multiple of a. For example, b is even, then 2 divides b is 0 even, is minus 4. The result on the divides operator, if a divides b and a divides c, then a divides b plus c. This is important result, and we can use this result directly in many problems. The example, 5 divides 25 and 5 divides 30, then 5 divides 25 plus 30. If a divides b, then a divides bc for all integers c, because c is the multiple of b. So here, if b is divisible by a, then automatically bc will be divisible by a. It means a divides bc for all integers c. Here is example, 25 is divisible by 5, but if we multiply any integer by 25, then that will be also divisible by 5. If a divides b and b divides c, then a divides c. This is also important result. For example, if 5 divides 25 and 25 divides 100, then 5 will definitely divide 100. The common facts, but good to repeat for background, like divides relation. For all a, b, c belongs to integer, a divides 0, a divides b, and a divides c, then a divides b plus c, a divides b, and for that a divides bc, and if a divides b and b divides c, then a divides c. The proof of the second, if a divides b, it means that there is an s such that b is equal to s, and a divides c means that there is t such that c equals 80. So b plus c is equal to s plus 80 is equal to a times s plus t. So a divides b plus c, and also the corollary is, if a, b, c are integers such that a divides b and a divides c, then a divides mb plus nc whenever m and n are integers. For detailed version of proof, so that for all a, b, c belongs to z, a divides b and continuously a divides c, then a divides b plus c. Let a, b, c be any integers such that A divides B and A divides C, and so that A divides B plus C. So by definition, we know that B is equal to AS and C is equal to AT. Let ST be any integer, then B plus C is equal to AS plus AT is equal to A times S plus T. So B plus C is equal to AU, and namely U is equal to S plus T. So A divides B plus C. This is the result for A, B and C.